We see metals every day. We think of them as these super solid, tough, unyielding materials, right? The steel in a skyscraper, the aluminum in your phone. But what if I told you that their greatest secrets and the real source of their strength are actually hidden deep inside, deep in a world of beautiful microscopic crystals? Okay, let's dive into the secret life of metals.
So, that's the big question, isn't it? What really gives metal its strength? And it seems simple, but the answer? Well, it takes us on this incredible journey from a fiery liquid to a solid structure that's both perfectly ordered and surprisingly flawed. It's not just about what it's made of, but how it's built, literally atom by atom. So here's the first major clue. A piece of metal is not just a solid blob of stuff. No. If you could zoom in way, way down to the atomic level, you'd see this. A tightly packed, perfectly ordered arrangement of atoms. It's a crystal structure. Think of them like perfectly stacked oranges at the grocery store, just forming these repeating 3D patterns over and over. This incredible order, that's the metal's natural state.
Okay, so where does this amazing internal architecture even come from? It doesn't just poof, appear out of nowhere. It actually grows, and the whole process starts when the metal is just a hot, formless liquid. As that molten metal starts to cool down, these tiny little solid specks begin to form. These are called nuclei. Picture this. You've got a huge, empty dance floor, and all of a sudden, a few people just start dancing in different spots, all on their own. Those first few dancers, those are our nuclei. They're the starting points for everything that comes next.
Now, from these initial seeds, the crystals don't just grow into neat little balls. No way. As you can see right here, they shoot outwards, forming these really intricate, branching, almost tree-like structures. They're called dendrites. It's kind of like watching frost spread across a window pane in winter, with each one reaching out to claim more territory in that surrounding liquid. So these branching dendrites, they just keep growing and expanding and reaching out until, bam, they run into each other. At that point, their growth is blocked. They can't go any further. And what we're left with is this amazing patchwork quilt of individual crystal regions. Each one of those patches, that's what we call a grain. And the line where two of these grains meet, this is fundamentally important. It's called a grain boundary. Now, it's not really a wall. It's more like a frontier region where the perfect repeating pattern of one crystal just bumps up against the slightly different angle of its neighbor. Seriously, tuck that term away, grain boundary. It is the secret key to absolutely everything we're about to talk about. Now, you'd probably think that a perfect, single, unbroken crystal would be the strongest possible metal, right? That just seems logical. But this is where things get really, really cool. The key to a metal's most useful properties, like its ability to be bent and shaped without snapping, lies not in its perfection, but actually in its flaws. You see, in the real world, those perfect stacks of atoms almost always have mistakes. And the most important type of mistake is called a dislocation. You can see it really clearly here in the diagram. It's like having an extra half row of seats just squeezed into a perfectly arranged theater. It doesn't belong, and this tiny imperfection creates a line of strain deep inside the crystal. So why does this little mistake matter so much? Well, because when you apply a force, when you try to bend a piece of metal, it's way, way easier for this one line of atoms to slip and move than for a whole giant sheet of atoms to shift all at once. The dislocation kind of moves through the crystal, like a ripple moving under a rug. And that movement, that is what allows a metal to bend and deform without just breaking. It's the source of its flexibility. And this is where it all clicks together. What stops that ripple in the rug? A wall, right? Well, in a metal, the grain boundaries act as those walls. When a moving dislocation hits a grain boundary, it pretty much gets stuck. It can't just cross into the next grain because all the rows of atoms are at a different angle. They don't line up. So this knowledge, it gives us an incredible power. I mean, think about it. If we know that grain boundaries stop these dislocations, and stopping the dislocations makes a metal harder to bend, in other words, makes it stronger, then we can start to actually engineer metals with the exact properties we want. This is the secret blacksmiths have known for centuries, now explained by science. All right, pop quiz time. Let's see if you're following along. Based on everything we've just learned, if you wanted to make a metal stronger, more resistant to bending, what would be your game plan? So what do you think? Would you A, try to make those grains as big as possible? Or maybe B, get rid of the boundaries altogether? How about C, create more grain boundaries? Or maybe D, heat the metal really, really slowly?
Think about it. What's going to create the most roadblocks for those little moving dislocations?
And the answer is C. If you said C, you absolutely nailed it. To make a metal stronger, you want to create more grain boundaries. More boundaries means more walls, which means it's just that much harder for those dislocations to move around. And that means you need more force to deform the metal. Simple as that.
Okay, so that naturally leads to the next big question, right? We know we want more grain boundaries to get a stronger metal. So how do we actually do that? How do we make more of them?
While it all comes down to controlling how fast the metal cools from a liquid. If you cool it really, really rapidly, a process blacksmiths call quenching, like plunging hot steel into water, you force tons of those little nuclei, seeds, to form all at once. With so many starting points, none of them have much room to grow before they bump into their neighbors. The result? Tiny little grains, and therefore a lot more grain boundaries. Slow cooling, of course, does the exact opposite. You get a few huge grains and not many boundaries.
So really, the whole thing boils down to this one simple, elegant relationship. Smaller grains means more barriers, and more barriers means a stronger metal. It's a principle that has let everyone from ancient blacksmiths to modern metallurgists forge materials with just incredible strength. And quenching isn't the only trick up our sleeve. There's another pretty clever method. You can actually seed the molten metal. That means you add a specific material right into the liquid, and these little added particles act as artificial nuclei. They give the crystals even more places to start growing from, which, you guessed it, also results in a finer, stronger grain structure. So in the end, the most important thing to remember is this. When you look at a solid piece of steel, its strength comes not just from the iron and carbon atoms it's made of, but from the invisible architecture built inside it. It's a vast, hidden landscape of tiny, imperfect crystals and the boundaries that hold them all together. And that kind of leaves us with a bigger thought to chew on, doesn't it? We've just seen that in the world of metals, a perfect, uniform structure is actually brittle and weak. Real strength and flexibility come from having internal boundaries and engineered flaws. It really makes you wonder, where else in life do we find that imperfections aren't a weakness, but the very source of resilience and strength? Okay, have you ever really, really looked at something simple, like a paper clip, or maybe the wire in a dental brace? We just see a piece of metal, right? But what if I told you that inside there's a whole secret world, a world of stress and strain, an incredible transformation happening on a microscopic level? Let's dive into the secret life of these stressed out metals all around us. So first things first, you gotta understand that metal isn't just one solid chunk. Nope, it's actually made up of millions and millions of tiny little microscopic crystals. We call them grains. Think of it like a wall made of countless tiny, tightly packed bricks. And just like with bricks, the size of these grains, their shape, how they're all arranged, that dictates everything. It's what makes a metal strong or soft or brittle or flexible. It's the whole secret right there. So what happens when we take that metal, say a wire for an orthodontic clasp, and we start bending it into the shape we want? Well, we're actually performing a process that completely changes that inner world of grains. It's a process called cold working. Now, the name cold working might throw you off. It doesn't mean we're doing this in a freezer or anything. It just means we're shaping the metal without a ton of heat. Specifically, we're staying below a certain critical temperature where the grains would try to reset themselves. You'll also hear it called work hardening, and honestly, that name really hits the nail on the head, as you're about to see. This is where it gets really cool. On the left, you can see the grains in their original, kind of relaxed, happy state. We call that equiaxed, which just means they're all pretty much equal-sided. But then, after we apply pressure and bend the metal, look what happens on the right. They get squished and stretched and elongated into this fibrous structure. It's like going from a loose pile of little building blocks to a bundle of uncooked spaghetti, all packed in tight and pointing in the same direction. So what does this actually do? Well, that new spaghetti-like structure makes the metal a lot stronger and harder. It's because all those tangled up grains make it really tough for any defects to move around, which is what allows metal to bend. So the yield stress, that's the force it takes to bend it for good, goes way up. But, and there's always a but, it's a trade-off. The metal becomes less ductile, meaning it's not as stretchy. And more importantly, it creates this invisible ticking time bomb inside the metal, internal stress. All right, quick pop quiz to make sure you're with me. The process of cold working makes a metal's grain structure more what? Take a second.
If you picked B, fibrous and strong, you're absolutely correct. We're squishing those relaxed grains into a tough, interwoven structure. Nice!
Okay, so we've made our metals stronger. That sounds awesome, right? But remember that little trade-off I mentioned? That invisible internal stress? Yeah, that is a serious problem just waiting to happen.
And this quote nails why it's such a big deal. That internal stress is basically like a tightly coiled spring that we've trapped inside the metal. And over time, that spring wants to uncoil. It wants to relax. And when it does, it causes the metal to warp and change shape. For something that needs to be super precise, like a dental clasp, even a tiny bit of distortion means it won't fit anymore. It becomes totally useless. So how do we fix this? How would we get rid of that dangerous coiled up stress without, losing the strength we just worked so hard to create? Well, the answer is heat. But it's not as simple as just torching it. It's about applying heat with incredible precision. And this is where the real art and science of metallurgy comes in. The temperature you choose is absolutely critical. It is literally the difference between giving the metal a gentle fix that just lets that internal stress relax and hitting a giant reset button that changes the whole grain structure back to what it was. So those two choices lead us down two totally different paths with very, very different results. The first path is called stress relief annealing. The second is recrystallization. Let's break them down. Okay, look at our two options here side by side. The biggest difference, the one that changes everything, is temperature. With stress relief annealing, you use a lower heat. Think of it like a targeted strike. You get rid of the stress, but you keep that strong fibrous shape. With recrystallization, you crank the heat way up. That's the total reset. The grains go back to being relaxed, and the metal becomes soft and stretchy again, but you lose all that extra strength you just built. So this first option, stress relief annealing, this is the perfect solution for our dental clasp problem. You heat it up gently, just enough to let that coiled spring of internal stress unwind and go away, but not hot enough to mess with the grain structure. You get to keep all that awesome strength and hardness from the cold working, but you completely eliminate the risk of it warping later. It's the best of both worlds. Now, our second option, recrystallization, is basically a softening treatment. By heating the metal much more intensely, you're pretty much erasing everything you just did with cold working. So why on earth would you do this? Well, what if you need to bend the metal even more? Recrystallization makes it soft and ductile again, so it's ready for another round of shaping. You just have to accept that you're sacrificing all the hardness you just gained. And this image just says it all, doesn't it? Recrystallization is literally taking that fibrous, stressed out grain structure on the left and letting it relax all the way back to its original equiaxed state on the right. It is the factory reset button for the metal's internal structure. It's like hitting Ctrl+Z on the whole process. But here's a quick and really important warning. You have to control this process very carefully. If you heat the metal for too long or get it too hot, the grains don't just reset, they actually start to grow bigger and bigger. And in the world of metallurgy, bigger grains almost always mean a weaker, less reliable metal. So precision here is everything. Okay, final quiz to tie this all together. You've cold worked a dental clasp. It's nice and strong, but it's full of stress. You need to keep that strength, but get rid of the stress. So which process are you going to use? The answer, of course, is C, stress relief annealing. That's how you get the strength you want without that dangerous internal stress. So now we can put all the pieces together. We can see the entire journey of creating a perfect, high-quality, reliable dental clasp from just a simple piece of wire to a finished, functional device. So here's the whole story in 4 steps. Step 1, you take the wire and you cold work it, bending it into shape, which makes it strong and hard. Step 2, in doing that, you've created the problem, internal stress. Step 3, you apply the solution, that gentle stress relief anneal. And the result? Exactly what the doctor ordered. A clasp that's strong, that holds its shape perfectly, and that isn't going to warp over time. It is a perfect, tiny example of material science in action. So the next time you see a piece of shaped wire, doesn't matter if it's holding your papers together or if it's part of a really sophisticated medical device, I hope you'll see it a little differently. Maybe you'll think about that hidden world inside, and you'll appreciate the incredible journey of stress and relief and transformation that all those tiny little grains have been on, just to become the perfect tool for the job.
You know, when you look around, you see metal everywhere, right? The fork in your kitchen, the body of a car, the massive frame of a skyscraper. You'd think they're all just made of plain old iron or aluminum. But here's the secret. They're not. Almost all of them are actually alloys. And today, we're going to pull back the curtain and see why these special mixtures are the hidden heroes of our modern world.
So think about this for a second. Why isn't an Olympic gold medal made of, 100% pure gold? It seems like it should be, right? Well, the truth is, pure gold is incredibly soft. I mean, so soft an athlete could literally bite down on it and leave a big old tooth mark. That softness is a huge problem for most pure metals. And it's the #1 reason we had to get creative and start mixing things up.
Okay, so how do we fix that whole too soft problem? The answer is alloys. In this first part, we're going to dig into what they actually are, and more importantly, how they end up being so much stronger than the individual metals they're made of.
At its heart, the definition couldn't be simpler. An alloy is just a mixture of 2 or more metals. That's it. You can kind of think of it like baking, but instead of mixing flour and sugar, metallurgists are mixing elements like copper and tin or iron and carbon to create a brand new material with totally different and usually much better properties.
So what's the big payoff for doing all this mixing? Well, you can see it right here. Pure metals, they're often pretty weak, pretty soft. But alloys, they're a whole different story. They're stronger, they're harder, and they have a higher elastic limit. That's just a fancy way of saying you can bend them more before they break, and they'll still snap right back into shape. It is a massive upgrade in performance.
Now, the science behind why this happens is so cool. It's called solution hardening. Just picture the atoms in a pure metal. They're all the same size, all lined up in these perfect, neat rows. Because they're so orderly, it's pretty easy for these rows to just slide past each other. But when you mix in some different-sized atoms from another metal, you mess up that perfect grid. These new atoms act like little obstacles, making it way harder for those rows to slip and slide. That internal resistance is what makes the whole material so much stronger.
Okay, so we know why we mix metals, to make them tougher. But what actually happens when you do it? When you take a molten, liquid mix of metals and let it cool down and become solid, it's not always straightforward. That mixture is heading for one of 4 possible outcomes. One of 4 fates, if you will.
And here they are, the 4 possibilities. The metals can mix together perfectly, they can totally separate, they can mix just a little bit, or they can actually react with each other and form something completely new. Let's break down what each of these means. First up, we have what you might call the perfect blend, complete solubility. This is when the different atoms just mix together perfectly and evenly, sharing a single crystal structure. The final product is called a solid solution, and it's a totally uniform material right down to the atomic level. Next, we have the complete opposite, total insolubility. Seriously, just think of oil and water. No matter how much you stir them, they're going to separate. Same thing can happen with metals. As the mix cools, they just refuse to blend, and they crystallize out separately. What's really interesting, though, is that this is actually pretty rare in the world of metals.
Now we get to the most common result of all. Partial solubility. This is the middle ground. A little bit of metal A dissolves into metal B, and a little bit of metal B dissolves into metal A. But for the most part, they stay in their own little distinct crystal regions. This compromises what happens in a ton of the alloys we use every day.
And finally, we have the most dramatic fate. Sometimes, the different atoms don't just physically mix together, they have a chemical reaction. They actually bond to form an entirely new substance, which we call an intermetallic compound. It's not a mixture anymore. It's a new material with its own strict chemical formula, like the one you see here. It has its own unique and often very useful properties.
All right, let's zoom back in on that first fate we talked about, the solid solution. This one is super important because it's the basis for so many common alloys. And it turns out, even when metals do mix perfectly, there are a few different ways their atoms can decide to arrange themselves.
So we've basically got 3 main flavors of solid solutions. The atoms can be scattered all over the place, totally random. They can line up in a very specific, ordered pattern, or you can have something called an interstitial solution. Let's really focus on the random and interstitial types.
The first one, random solid solution, is, well, it's exactly what it sounds like. The atoms from the different metals are just scattered all throughout the crystal structure, with no rhyme or reason. The analogy of a mixed bowl of candy is perfect. You've just got different kinds all jumbled up together. Simple as that.
The second type is the interstitial solid solution, and this is where things get really clever. This can only happen when one type of atom is much, much smaller than the other. The little atoms don't actually replace the big ones. Instead, they tuck themselves into the natural little gaps, the interstices, that exist between the bigger atoms. Think about pouring sand into a jar of marbles. The sand doesn't kick the marbles out. It just fills in all the empty space. This is exactly how we make steel. Tiny little carbon atoms are squeezed into the gaps between the much larger iron atoms, and that's what makes steel so incredibly strong.
Okay, one last major concept to wrap our heads around, and it's all about the cooling process. You see, the way an alloy freezes is fundamentally different from how a pure metal freezes, and that difference changes everything about the final material.
So here it is, the key takeaway. A pure metal, like pure water turning into pure ice, freezes at one single specific temperature. But an alloy? It doesn't do that. It freezes slowly, over a whole range of temperatures. It starts getting solid at a higher temperature, and it only becomes fully frozen at a lower one.
And these graphs show us exactly what's going on. Look over on the left, at graph A for the pure metal. See that long, totally flat line? That's the freezing point. All the liquid turns to solid at that one constant temperature. Now look at graph B, the alloy. See, there's no flat line at all. Instead, the slope of the curve changes. It solidifies gradually over that whole temperature range, from T1 down to T2. That freezing range is the crucial difference.
And a direct result of that gradual freezing is something we call a chord structure. Because the parts of the alloy with a higher melting point freeze first, the center of each little crystal grain ends up having a different chemical makeup than the outer edges, which freeze last. It's kind of like a microscopic jawbreaker with different layers of composition from the inside out.
All right, we have covered a ton of ground here. So before we wrap up, it's time to see what you've learned. Let's do one quick question to test your mettle.
Okay, here we go. What do we call it when those small atoms fit into the spaces between larger atoms? Is it A, random solution, B, chord structure, C, interstitial solution, or D, ordered solution? Take a second to think about it.
And if you said C, interstitial solution, you are absolutely right. The clue is right there in the name. The smaller atoms fill the interstices, which is just the scientific word for those gaps. Nice work.
So there you have it, a quick dive into the science of the mix. When you think about it, from the very first bronze tools that kicked off a whole new age of civilization, to the incredible superalloys inside a modern jet engine, these mixtures have literally defined human progress. It really just leaves you with one big question, right? What's the next great material mixture going to be?
Have you ever wondered how we create the perfect metal for something like a jet engine, or maybe even a filling in your tooth? Well, it turns out there's a secret world behind it all. Today, we're going to uncover the hidden maps that scientists and engineers use to literally design the materials that build our world. So let's dive in.
So, what is the recipe for an alloy? You'd think it's simple, right? Just melt down, say, 60% copper and 40% zinc, and bam, you've got brass. But it's not that easy. Turns out, the final properties of that metal depend entirely on what happens as it cools down. To figure that out, you need a very special kind of map. A map that charts the very states of matter. And these incredible guides are called phase diagrams. Now, I want you to think of a phase diagram as a treasure map for an alloy. But instead of X marks the spot for gold, it shows you exactly what form, or phase, the alloy is in at any temperature for any mix of ingredients. And these aren't just some theoretical drawings. Scientists build them piece by painstaking piece from real experimental data. So how in the world do you actually make one? Well, it all starts with just watching things cool down. Seriously. Scientists mix up a whole bunch of alloys, 80% of metal A and 20% of metal B, then 60-40, then 50-50, and so on. They melt each one down and then just watch, carefully noting the exact temperature where it starts to freeze and the temperature where it finally becomes completely solid. Okay, so this is where all those notes start to look like a map. You take all those data points and you plot them on a graph. The up and down axis is temperature, and the side-to-side axis is the composition, going from 100% metal A on the left to 100% metal B on the right. T1, where freezing starts, and T2, where it ends, get plotted for every single mixture. And when you start connecting those dots, well, you can see the shape of our map starting to emerge.
All right, let's start with the simplest kind of map. It's for what we call a solid solution system. This is basically where two metals are best friends. They're perfectly happy to mix together in any amount when they're solid. The best analogy? It's just like how sugar completely disappears when you stir it into water. They form one single, uniform material. And voila, here's the finished map. You connect all those start freezing points, those T1s, and you get the top line. You connect all the finish freezing T2 points, you get the bottom line. And just like that, those two lines divide our map into 3 totally distinct regions. This is so powerful, because now you can find the state of any combination of A and B at any temperature, just by finding its coordinates.
So let's look at the landmarks. That top line is called the liquidus line. A good way to think of it is as the coastline of a continent. If your alloy's temperature and composition puts you anywhere above this line, you're out in the deep blue ocean. It's 100% liquid.
And that bottom line, that's the solidus line. If the liquidus is the coastline, this is the shoreline. If your alloy's coordinates are anywhere below this line, you're on solid ground. It has completely frozen into a solid.
But what about that space in between the two lines? Now that's where things get really interesting. This is like the tidal zone, right? The alloy here isn't fully liquid, but it's not fully solid either. It's a slushy, mushy mix of solid crystals starting to form inside the leftover liquid metal. Okay, pop quiz. Let's see if you've got this. Remember our 3 zones, the liquid ocean up top, the solid land down below, and that slushy zone in the middle. If we pick a point for our alloy that lands smack in that middle region, what state is it in? Yep, you got it. It's C, a mix of liquid and solid. See? Once you know how to read the map, you can predict its state every single time. Now these maps are awesome, but they're drawn with one big assumption, that the alloy cools down really, really slowly, giving everything time to get perfectly arranged. But the real world? It's usually in a rush, and cooling things down fast introduces a really fascinating wrinkle into the whole process.
And that wrinkle has a name. It's called coring. See, when you cool an alloy down super fast, the atoms just don't have time to move around and mix evenly. So the very first solid bits that form are richer in the metal that has the higher melting point. Then, as it keeps cooling, new layers freeze around those first bits, each with a slightly different recipe. What you end up with is kind of like microscopic tree rings inside the metal.
And here's the cool part. Our map can actually predict this. Take a look at diagram A on the left. See how there's a really wide gap between the liquidus and solidus lines? That big gap means there's a huge difference in composition between the first solid that freezes and the last liquid that freezes. And that means you're going to get a lot of coring. Now look at diagram B. The lines are much closer. A smaller gap means less coring. Simple as that. So everything we've looked at so far is a world where our metals get along, right? They're like sugar and water. But what if they don't? What if they're more like oil and water? They might mix just fine when they're liquid, but the second they start to solidify, they want nothing to do with each other. This creates a whole new kind of map for what's called a eutectic system. So let's just make the difference crystal clear. In our solid solution on the left, the atoms all mingle together to make one uniform solid. But on the right, in a eutectic system, the solid metals just refuse to mix. So as they freeze, they separate out into this microscopic mixture of 2 totally different solid phases. Think of it like a superfine layered crystal structure. And here is the map for a eutectic system. Whoa, right? It looks completely different. You've got this big, distinct V shape. And right there at the very bottom of the V, there's a new, super important landmark called the eutectic point. You see it labeled there as C? That little point is the absolute key to understanding this entire map. Let's trace a journey on this new map, okay? Let's say we have an alloy with the composition marked X, and we start cooling it down from a liquid. As it crosses that first line, little solid crystals of pure metal A start popping up. It keeps cooling, more crystals form, but then when it hits that flat horizontal line, something amazing happens. All of the liquid that's left, bam, it instantly freezes into a fine-grained mixture of both solid A and solid B. So we've gone through these pretty complex maps, but why? What's the point? Why go to all this trouble charting these metallic landscapes? The answer is simple, because if you understand these maps, you gain the power to design and control the properties of materials right from the atomic level. The secret is all about that special spot, the eutectic point. An alloy with that exact recipe is totally unique.
As the quote says, it acts just like a pure metal. And what that means is it doesn't have a slushy freezing range at all. It goes from solid to liquid at one single sharp temperature. And that one property? It's a total game changer. Think about solder for electronics. You need something that melts at a low, super predictable temperature, so you can join parts without melting the whole circuit board. A eutectic alloy is perfect. It snaps from solid to liquid instantly. Or how about in dentistry? These maps are absolutely critical for designing fillings that have the perfect strength, won't corrode, and behave just right. So at the end of the day, that's what this is all about. Phase diagrams aren't just some abstract drawings in a textbook. They're incredibly powerful predictive tools. By reading these maps, we can figure out why an old alloy works the way it does. And even better, we can design brand new materials with exactly the properties we need for pretty much any application you can dream of. These maps peel back the curtain and show us the fundamental rules that govern the hidden world of metals. It really makes you think, doesn't it? What other complex, invisible structures all around us, from the connections in our own brains to our social networks, are we just now finally learning how to map?